All right, I think so. So welcome everyone. I'm super glad today for like another episode of GPU Mode, and today our guest is Songlin Yang. So Songlin actually was like recommended to come in as a speaker to me by like multiple people. And the main reason being that like what kind of makes a lot of what we do in the server around like writing custom kernels interesting is exploring atypical architectures. And Songlin has been one of the sort of the really key people in the research community, building efficient architectures and also like making them faster. So I thought you should all love to hear from her, and I'm certainly very excited for this talk. So yeah, Songlin, please take it from here.
Yeah, thank you for having me today. And today I'll be presenting hardware efficient training of linear attention, delta net, and beyond. So first off, we have the transformer, which is the workhorse of modern generative AI. And we all know that the softmax attention mechanism. So here is a quick recap of it. For parallel training, we have three matrices, Q, K, V, of size L by D. L is the for sequence length, and the D is the head dimension. We only discuss a single head here. And M is the quadron mask. So for parallel training, we can use several dot product. So first we take the dot product between the query and the key matrix to obtain the attention logit. And then we apply the quadron mask, followed by a softmax operator. And finally, we take another dot product between the resulting self-attention matrix and the value matrix to obtain the output. This is for parallel training. In this scenario, we have the input sequence. For autoregressive generation, we have the iterative form. So basically, at time step t, we use that time steps query qt to attend the previous key vectors, so that we can have our attention score. And then we use this attention score to take the weighted sum of the historical values to obtain the output. Okay, this is a very quick recap of the softmax attention mechanism, and I'm pretty sure everyone is super familiar with it, so I'm not going to introduce more about attention mechanism. And we all know that for softmax attention, it has several efficiency issues. The first one lies in the training efficiency due to the quadratic scaling of the softmax attention mechanism. And this could be very problematic when the sequence length is like really large. For example, when the sequence length is like in the million level, which is often the case in video generation or DNA or RNA modeling. And in this application scenario, the self-attention mechanism tend to be the key bottleneck. The second efficiency issue, it lies in the inference. And in inference, we need to maintain the historical key and the value vectors, which is so-called the KV cache. Its KV cache size grows linearly with respect to the generation length. So in this sense, if we want to do long generation, and the KV cache size will like tend to blow up and leading to some memory out of memory issue. Okay, now we understand the key efficiency challenge of self-attention mechanism, and I'm pretty sure there are lots of different optimization techniques for reducing this cost. But today, I'll be focusing on a different architecture that can remove the KV cache from the first principle. So it is the so-called linear attention. And the key idea behind linear attention is really simple. And so it basically, we have the softmax attention, and what linear attention does is to remove the softmax operator. And so we can have this iterative form. Let's dig into it. So here we have this attention score. We don't have the softmax operator, and now it is fully linear operator because we remove the softmax operator. And first, this is a scalar value, and we put this scalar value to the second position. And then we leverage the associativity property of these linear operators to compose the value and the key first. So we have this term colored in red, and it is a cumulative sum of the keys and the auto product between the keys and the values in the for all historical steps. And this this term colored in red is often referred to as the iron's hidden state, because in this sense, this hidden state encodes the key value association pair into this recurrent memory using this outer product computation structure. Now it becomes very clear that linear attention implements linear recurrence. So the recurrent state update is a very simple cumulative sum of this outer product between the keys and values. For output computation, we use matrix vector multiplication to obtain the output. And this is a really simple linear recurrence. And we also know that in this case, the recurrent hidden state is of size d by d. In classical arms like LSTMs and gated recurrent unit, the recurrent state size is often in the scale of d, which is the input dimension. And now the recurrent state size is in the scale of d square. So in this sense, linear attention has a mechanism that allows us to scale up the recurrent state size in a very efficient manner. And we all know, like for irons, the recurrent state size is like super important, because irons only has a fixed state size, state memory to encode all of the historical data. And intuitively, the larger the state size, the better the memory capacity of this iron. Next, I'll be discussing how to train this linear attention model in a hardware efficient manner. So previously, we have shown the parallel form and the recurrent form of linear attention. However, unfortunately, both forms are not suitable for hardware efficient training. So first of all, the parallel form, it is like a very similar to the linear soft Mesa attention case, and it also scales quadratically with respect to the sequenceless, which is very problematic if we do very long sequence modeling. For the recurrent form, it is also problematic. Because for several reasons. The first reason is that in recurrent form, we have to do this sequential recurrence, which limits the parallelism across the sequenceless dimension. This recurrent form is like very, you need to do it in a sequential manner. And secondly, we can see, for this recurrent state update, we only involve a rank 1 outer product update. And for memory readout, we only have a matrix vector multiplications, both of which are not matrix multiplication. And these two operations cannot use tensor cores. And this is why these operations cannot be accelerated by the tensor core, which is like very efficient. A common question is that why don't we use the parallel scan to train this linear attention model? Because the first limitation of the recurrent form is that it cannot parallelize across the sequence length. But this is a linear recurrence, and we all know that the linear recurrence can be parallelized across the sequence length using the parallel scan algorithm. But in the linear attention case, parallel scan can provide sequence level parallelism. You can do parallel computation for different trunk of data. However, if you just use the parallel scan algorithm to train linear attention, you still do not have the those operations that allow you to do fast multiplication on GPUs. basically because this is due to the limitation of the recurrent form. It just does not have the matrix multiply based update mechanism. This could be problematic when scaling up the recurrent state size. And for this reason, member 1 cannot scale its state size in a hardware efficient manner because it cannot leverage the tensor cores. Finally, the parallel scan tends to incur a very large memory and I/O overhead. We can see a thread. So for recurrent form, we only need to maintain a single recurrent state of size d by d. But for parallel scan, especially when the state size is like too large, we cannot fit it into the shared memory. So we must materialize it into the HBM, and this is where you need to maintain a lot of recurrent state size, and this is like super memory consuming because as we mentioned before, we have a linear attention implements a state expansion mechanism, and for each position, the recurrent state size is like of d by d. And if we materialize the recurrent state size for every single time step, the memory complexity is like OL times d square, which is like d times larger than the query vector or the key vector, and this is not acceptable. And for these reasons, parallel scan is just too slow in practice to train this linear attention mechanism and models. So due to the limitations of the recurrent and the parallel form, we discuss the Chunkwise form, which is basically an intermediate form sitting between the recurrent form and the parallel form. So the high-level idea of Chunkwise algorithm is that if first we have a sequence and we have a trunk size C, we split the sequence into several trunks of equal size. When the trunk size equals to 1, we can recover the recurrent update mechanism. And when the trunk size equals to the 4 sequence lengths, it will reduce to the parallel form. And here I also want to emphasize that the Chunkwise form is not an approximation. Yeah, it is like mathematically equivalent to the recurrent form and the parallel form. Because linear attention is like, there are a lot of linear operations and allow us to leverage the associativity property to do these mathematical transformations. In Chunkwise form, we instead of computing the recurrent state for every single token, we only compute the recurrent state for each trunk and potentially materialize them onto the HBM. And then we can use a hybrid form to compute the desired output. So for historical context, since we already encode all of the historical information into the trunk level hidden state, then we can leverage this recurrent form to compute the output contributed from the previous context. And for the local context, since we do not have the recurrent state, then we can resort to the parallel form to directly compute the output contributed by the local trunks context. This is the high-level idea of Chunkwise form. To formulate it mathematically, we have several notations. So first, this is the trunk level hidden state, and we use this subscript with bracket to indicate this number indicates the index of the trunk. And also we have these notations to denote the sub-block for query key value and the output matrix. So they are of size C by D. The full matrix is of size L by D, but now we only take its sub-block to consider the computation of the trunk I. So first off, in the first step, we have the trunk level recurrent state computation. So in this stage, we only compute the recurrent state for each trunk, which is basically the last position of each trunk. And we directly jump from this state to this state. And in the middle, we have several state, but we skip the computation. We just directly jump to the last state. For this recurrent state update, we need to do the cumulative sum of the outer product between the key and the value vector for this very trunk. And there's a very elegant mathematical property. So the cumulative sum of this outer product could be written in matrix multiplication. And this is why we can write this recurrent state update in matrix multiplication. So here we have the key block and the value block of size C by D. And we take the transpose of the value block, and then we take the dot product and we marginalize over this trunk size dimension. So we will obtain a D by D output, which is of the same size as the recurrent hidden state. Then we just sum up these two terms to achieve this state update. For the output computation, like we mentioned before, we have two sources of contribution. The first, we have the historical context, which was summarized into the last trunk's hidden state. So for these trunks, we can leverage the recurrent form. For each query, we can attend to this recurrent state to obtain the output. And since we have multiple queries in this trunk, and they are retrieving an output from the same recurrent state, so this is like a batchification computation. So we can do the batchification in the query's sequence dimension to have a matrix multiplication. So the first term is of size C by D, and the second term is D by D. So we can rewrite this process as a matrix multiplication. This is the inter-trunk contribution. We compute the output contributed by the previous context. And the second, we also need to consider the output contributed by the current local trunk. And in such scenario, we just leverage the parallel form to directly compute the output based on the input, query, key, and value. We do not need to compute any intermediate recurrent state. We can just compute the output based on the input data. And this is very similar to the parallel form of the self-attention mechanism. Yeah, this is like a local trunk linear attention. We apply this parallel linear attention form to each trunk separately. To summarize, with this trunkwise form and with the fixed trunk size C, the overall time complexity is OL d squared plus OL dc, which is subquadratic when this C does not grow with respect to the sequence length L. And in practice, we set C to a small constant that allows us to do hardware efficient computation. For example, 64, 128, and 256. These are very common block size when we write some matrix multiplication kernel. This trunkwise form is also very general. We can extend this trunkwise algorithm to have hardware efficient training of different linear attention variants, like linear attention with decay, for example, Mamba2, and also linear attention with the delta rule, which we will introduce later. And this trunkwise algorithm has been the standard training technique for modern linear attention models, like Mamba2 based Delta Net, MSTMs, among others. We also have so for Chunkwise form, we have a algorithm that is very aligning to the modern hardware, but we also need to do some I/O optimization to further increase to improve the workload time. And in flash linear attention, we do several kernel fusion to try to reduce the I/O cost. Because, like for example, in this case, this query block could be used to compute both the output and also the output for the for the two parts of the output contributed by the previous context and the local context. For the key block, it could be used to compute to update the hidden state, and it also could be used to compute the output from the local context. Yeah, so this is like a simple kernel fusion to reduce the I/O cost. And in practice, this kernel fusion can lead to a significant speed up on modern hardware on GPUs. It's like you can need to like 4 times speed up comparing to the one in the PyTorch implementation. And we also have an open source library called Flash Linear Attention. And in this library, we provide lots of implementations of different linear attention mechanisms, like RANlet, GLA-based RWKV, stuff like that. And to summarize, in the linear attention, the concept of linear attention is quite simple. It's just softmax attention without softmax operator. And it could be formulated as a linear R with matrix valued hidden state. This allows you to have more recurrent state to encode the historical data. And the Chunkwise parallel form is the hardware efficient algorithm to train these linear attention models. And flash linear attention is an I/O-aware implementation of this Chunkwise parallel form. Okay, now we are good with the some basic optimization techniques of the linear attention. However, linear attention itself has several performance issues, especially in this in-context retrieval. So we have multiple papers to show that this linear attention or RNN or state space model, whatever, and they are all limited to some common issue like in context retrieval due to the limited state size. So this is also very intuitive because you cannot expect the RNN to encode all the historical data in a lossless manner, right? Because the recurrent hidden state is fixed in size. So because these methods are very perform very poorly in context retrieval, and in context retrieval is very important for downstream task. So in previous, I want to come up with a model to impose the in-context recall of these linear RNNs, which is the Delta Net. And I'm going to introduce the Delta Net in this session. So first, we can analyze why linear attention performs poorly in context recall. Like we said before, linear attention could be regarded as an associative memory, encoding the key value association pair using this outer product structure. This is very correlated to the classical associative memory. And if we want to use a key, we use key to retrieve the output from this recurrent memory, and we use this memory readout operation to retrieve the output. And we can see because this kj is associated with the value at the s time step. So ideally, we want to retrieve vj from this recurrent memory. Because in this associative memory, we have other key value association pairs, so we have some unwanted cross terms, which is colored in orange. And I refer to this cross term as the retrieval error because this is the term we do not want from this record memory. This is because if we want to do perfect retrieval, all of the key vectors should be orthogonal to each other, and then we can do this perfect retrieval. But because the associative memory is of d by d, so there are up to d number of association, d number of orthogonal vectors in this vector space, and this retrieval error is inevitable when the sequence length is larger than the model dimension. And this is why increasing the height dimension is very useful because if we increase the height dimension, there are more room to have more orthogonal key vectors in this vector space, and then we can have more better retrieval performance. And this is a fundamental limitation of linear attention. So we want to design some mechanism to elevate this issue. And here we have the Delta Net. Delta Net is actually a classical model proposed by Dan, and they use a very intuitive memory update mechanism. So we have the query key and the value vectors is very similar to linear attention or supervised attention. We have several linear projections on the input data to obtain query key and the value vectors. And in Delta Net, we also have another linear projection mapping the input token to a scalar value. And we also apply the sigmoid function to restrict this value to 0 and 1. And this beta t could be imagined as the writing strength of the current input. Delta Net has a memory management mechanism that the final input is computed by the weighted sum of the new input and the old value. This old value is computed in this way. So we use this input key to retrieve the associated value from this recurrent memory. And then the model dynamically decides whether to use the new associated value, which is the input value colored in green. And we also have some old associated value colored in blue. And the model must decide whether we use the previous associated value or the current associated value. So we have this beta t to control this process, and this beta t is data dependent. So the model can dynamically decide to learn to retain the current value or to use the previous associated value. And then in Delta Net, it erases the old value from this recurrent memory, and then it writes the new key value association information into this recurrent memory. And this update mechanism is a key to achieve very good associative recall performance. For the memory readout, it is the same as vanilla linear attention. We have a matrix vector multiplication to do so. So here we have a very toy-rich benchmark called the multi-query associative recall. This is a synthetic benchmark to test the in-context retrieval performance of these emerging architectures. This task is very simple. So we have multiple key value pairs provided in the pairs context. The keys are the capital letter, and the values are numbers. So we have these key value pairs in the pairs context, and the model needs to retrieve the values based on the keys from the pairs context. And this is a purely in-context learning task because the answer is only provided in the pairs context. It is not provided in in the previous training data, and this training data is constructed on the fly. So model have no way to encode this associative pair in its like a feed-forward memory. And although this task is very toy-rich, very simple, the softmax transformer can solve this task perfectly. But for other subprojective model like Mamba, GLA, RedNet, when the model dimension is small, it cannot achieve the perfect performance. We also have discussed before, because like when the model dimension is small and the model can only have a small number of orthogonal key vectors in that vector space, and this is where the model can have a larger retrieval error. But for Delta Net, it has a better memory management mechanism, allowing Delta Net to have perfect performance even when the model dimension is small. Okay, now we know that Delta Net is performance very strong in context retrieval. Let's I'll connect Delta Net to some very recent concept called test time training or test time regression. So here we have a very elegant framework called test time regression. It categorized many recent self-projective sequence modeling area into several categories. And DataNet has an online learning objective, and it used the stochastic gradient descent to optimize the online learning objective. And so the online learning objective of DataNet is this linear regression nodes between the transferred key and the values. So in this case, the recurrent hidden state S is regarded as the weight matrix. This view also has a very interesting connection to the fast-way programming. So the recurrent state of the R can be viewed as the fast weight. By fast weight, it changes every single step. And the test time training framework also has this interpretation. So it regards this recurrent state as this weight matrix, and so we use this weight matrix to do this like linear transformation, and then we want to recover the input value. And this is a linear regression loss function. And if we take the single step of gradient descent on this objective function, and we will recover the data net update rule. So this beta t here is the learning rate from the perspective of online gradient descent. In the previous context, this beta t is the writing strength, controlling whether how many information we want to preserve for the historical associated value, and how many information we want to new information we want to use for the new incoming input value. So here we can recover the data net update rule. And also a common question is that why should we use this online learning objective? This is a common question I've encountered for my previous talks. And here I give you a very intuitive understanding of this objective because, for in-context learning, we want to use the some key value association pair provided in the previous context. So for softmax attention, it uses the KV cache to directly store this key value association pair for later usage. However, for ARNs, it does not have the KV cache to store this in-context information. And then we would want the ARN's recurrent hidden state to encode those key value associative pair for the previous context. And we want to encourage the ARN to encode those key value pairs as accurate as possible. So if we have this learning objective, the R model directly optimize this key value association and prediction rules, and so hopefully it can better memorize this key and value pairs. So this is like a very intuitive understanding why we want to optimize these linear regression rules between these key value pairs. And next, I'll be briefly discussing the parallel training of Delta Net. So by rearranging the Delta Net's linear recurrence, we can obtain this form. I skip several derivations. So this is the final linear recurrence form of Delta Net. And we can also write it into a form that is very similar to the vanilla linear tension. And so here, as long we can compute this UT in a very efficient manner, then we can leverage the linear tension kernel as we discussed before for hardware efficient training. So first off, if we want to train R in parallel, we need to unroll this recurrence. And by unrolling the recurrence, we will have the cumulative product of this transition matrix. And in the Delta Net case, we also have this cumulative product of the transition matrix, and which is colored in blue. For arbitrary RNs, if we have an arbitrary transition matrix of size d by d, and this cumulative product computation will be very computational intensive. However, for Delta Net, because it uses structured transition matrix, this matrix is of form identity plus low rank. And in this case, there are existing algorithms for fast computation. For example, this form is like very similar to the well-known householder matrix. When this beta j equals to 2, and this case are L2 normalized, we can have those householder matrix. And the cumulative product of the householder matrix has been well studied in the numerical linear algebra literature. And in this work, we leverage a classical algorithm called the WY representation to compute the cumulative product of this householder-like matrix in a hardware efficient manner. Yeah, so a two-known theory is that we can rewrite this cumulative product as cumulative sum using this WY representation. This makes the optimization much more easier because this cumulative sum of the outer product could be written in matrix multiplication in very easily. This is like very similar to the linear tension state update rule before, and we will show that okay, this cumulative sum of this outer product could be written in matrix multiplication. So we can adapt the linear tension's Chunkwise algorithm to the Delta Net case. So first off, for the state update, we need to consider the state transition matrix as well. So for the vanilla linear tension, we can view the state transition matrix as the identity matrix. So it basically does nothing. And however, in this case, we need to take into account this cumulative product of the transition matrix. And here we need to take the cumulative product of the transition matrix within this trunk, and this could be written in this form because here we have a conclusion. And we can also write it into the matrix multiplication form, so we can have this state update matrix multiplication. And also, we can leverage another well-known technique called the UT transform to compute this W vector and the input U vector in a very hardware efficient manner. So I don't want to talk this in detail because it's kind of like heavy in math, but the key intuition is that we can solve, here we can use some matrix multiplication to obtain this C by C matrix. And then we take its loyal triangle, and we make the diagonal elements to be 1, and we solve this loyal triangle matrix. We can use the forward substitution to compute this matrix inverse. And then once this C by C matrix was computed, we can compute this W and this mu U matrix using matrix multiplication. Yeah, so if you are interested in the derivation, you can read my blog post for more details. I have a blog post to derive this algorithm in detail. For the parallel output computation, it is very similar to the linear attention case, except that we need to consider the influence from the previous hidden state, because in delta net, the input value is influenced by the previous hidden state. And we use another matrix multiplication to address the input value matrix. So this matrix is the UT matrix we want. Yeah. So this is the algorithm. We can compute that U vector in a Chunkwise hardware efficient manner. Yeah, this is the key idea of the delta net Chunkwise computation. And here we have a speed comparison. So for this is a speed comparison between the Chunkwise kernel and the pure recurrent kernel. We can see that with the increase of the height dimension and with the increase of the sequenceness, the speed up becomes more significant. And this is not surprising, because like when increasing the sequenceness, we want to use more sequence level parallelism to tackle this computation. For recurrent form, it has to compute it in a sequential manner, but for Chunkwise form, we can parallelize the computation over the sequenceness. For a larger height dimension, we know that by increasing the height dimension, the total amount of flops has been increased. And if we can write this computation into matrix multiplication, then we can use tensor cores to better optimize these flops. And here is like overview of the end-to-end training throughput of several models. We can see delta net has a satisfactory training throughput, although it has a more complicated state transition matrix. Finally, I want to mention the gated delta net, which is my last year's Eclair work. I combined the Mamba2 gating mechanism and the delta net transition matrix into a single update rule, the so-called gated delta update rule. And this combination can further improve the delta net by a large margin. Okay, finally, I'll briefly discuss several extensions of delta rule. So first off, we have the test-time training layer. In delta net, we have the linear regression objective, which is it has a assumption that the input data is linearly dependent to each other, which is not often the case. So we want to use this nonlinear regression objective to optimize this function. Yeah, by using this nonlinear regression objective, this resulting model is definitely more expressive. For example, in TT layer, they have several variants. And this FS is a nonlinear transformation parameterized by the recurrent hidden state. Yeah, so this recurrent hidden state is the fast rate of another neural network. And this is also very correlated to the fast rate programming literature. And they have several variants. The first variant is the so-called TT linear, and it is like very similar to delta net, except that this output is followed by a layer-long nonlinear function. So the resulting TT linear model is a nonlinear model. They also have several very expressive variants. For example, TT MLP, they use multi-layer perception to encode this. As this nonlinear transformation, which makes the model more expressive. However, because the nonlinear associative the nonlinear objective function, so if we apply the single step gradient descent to obtain the recurrence, the resulting recurrence would be nonlinear because the objective function is nonlinear. And we all know that for nonlinears, we cannot parallelize it across the sequence length. And this could be very problematic. We have to resort to the recurrent form for training, which is not acceptable. To work around this issue, in TDT, they come up with a mechanism called the mini batch gradient descent. So for Delta Net, it applies online gradient descent to optimize the objective. So the weight matrix or the recurrent state is updated for each time step. But in TDT, they use a mini batch gradient descent step. So the mini batch is like the trunk size. And so they only update the recurrent state after processing several tokens. And the number of tokens is the same as this mini batch size. And each token within this trunk is treated as an independent training example for parallel processing. And by doing so, okay, we can process multiple tokens at once. However, we lose the sequential dependency for tokens within the same trunk because each token within the trunk is treated as an independent training example. So we don't have the sequential dependency. So to work around with this problem, they also come up with a hybrid strategy. So they combine this the inter-trunk linear recurrence with the intra-trunk linear recurrence. For each trunk, they apply a very lightweight linear recurrence to build the sequential dependency within each trunk. And this is the high-level idea of the TT's training strategy. It is a bit complicated. And this framework has been extended to a lot of follow-up work, like in Titans. They come up, they use the same objective function, and they use the same parameterization of this FS. The only difference of Titans is that they improve the optimization technique of this gradient descent process. So for TDT, they use the nonlinear stochastic gradient descent to optimize this nonlinear objective function. But in Titans, they use SGD with momentum and the weight decay term to optimize this process. And we all know that the momentum term and the weight decay term have been widely used in stochastic gradient descent optimization. And this is why they can achieve better performance. So they have a better optimizer to optimize this more complicated objective function. And finally, I want to briefly mention several work. So first off, it is called the TDT downright work. It is a joint work with Tian Yuan. In this work, we found that okay, this TDT training framework we already show here, and they have they need to have a trunk size, and the larger the trunk size, the worse the performance, right? Because when increasing the trunk size, the recurrent update frequency becomes less, and this is bad for the performance. But we just think that okay, we can use a trunk softmax attention. So it doesn't matter if we update the recurrent state in a less frequent manner. And then by incorporating the trunk attention, we can have a much larger trunk size for this recurrent update. And the recurrent memory can be used to purely encode the historical information. So this allows us to have some less frequent recurrent state update room. Sorry. And then we can increase the trunk size by we can have a very large trunk size. So this is the large trunk TDT framework. So the trunk size in the original TDT paper is very small. It is like 16. And because the TDT update is also very complicated, so it is like very hard to optimize on modern GPUs. But with a very large trunk size, we can even write a pure PyTorch code to compute this large trunk TDT update mechanism. And here we have some GPU throughput comparison. We can see that TDT linear was very slow on A100. Yeah, I know these TDT models are very can be very fast on TPUs, but for GPUs they are very slow. And we can see here we have the throughput comparison, and this TDT linear and TDT MLP is like super slow on GPUs. And so by using this large trunk TDT framework, it allows us to have a way to better scaling up the recurrent state size. And also we can use other fancier optimization technique, like in this work, we use Muon, a new emerging optimizer to do this online gradient descent. And this is the work of TT downright. And the next, I'll also briefly discuss another recent work called Mesa layer. So for Delta Net and TTT, the training objective is just the linear regression loss or nonlinear regression loss for the current key value association pair. However, it does not consider the entire history of the key value association pair. So in Mesa layer, in the objective function, it also considers the key value association pair for the entire history. So here we have the objective function. So for time step t, the objective considers the entire history from the very first beginning of the sequence up to the current time step. So we also have the forgetting weight to weight more on the recent past. And yeah, this is a common strategy in the in this online learning literature. And also we have a regularization term to try to regularize the recurrent norm, the norm of the recurrent state. And this online learning objective is very classical. It is basically the the recursive least square algorithms objective. And we can have the closed form solution for this update. So here we have these two hidden state. The first one is very similar to some sort of gated version of linear attention. And we also have another state that try to compute this key covariance matrix. And for the output computation, we can, for the memory readout, we can use this strategy to compute the output. And this is a very interesting mechanism that allow you to have a more informed online learning objective to consider the entire history. And in this recent work, which was archived like 2 days ago, we have a new paper trying to up this Mesa Net. And previously, here we have the matrix inverse operator, which is very hardware inefficient to compute for each position. And in this paper, we use the conjugate gradient descent method to compute this matrix inverse term. And this conjugate gradient method could be, it is totally compatible with the Chunkwise parallel training algorithm as we introduced in the previous context, and making the resulting Mesa Net very scalable. Yeah. So this is for the first time we can train this very interesting sequence modeling layer in a hardware efficient manner. Yeah, and thank you for listening. And yeah.
Cool. Thank you so much, Songlin. This is really awesome. I love that you gave us like a very large tour. It reminded me of my grad school days, like doing linear algebra classes. So I guess like my high level sort of question is, at least as far as like a lot of people in the GPU mode server are mostly interested in infrastructure and making this kind of research more accessible. Do you have like any sense of like what kinds of things, what kinds of like lower level pieces of infrastructure would make your research easier to do?
Yeah, I think for new sequence modeling, so yeah, we all know that we have a large community try to have some new sequence modeling layer, right? And currently, I'm implementing all these layers in Triton. Yeah, Triton is very easy to write for machine learning practitioners. However, Triton is also very limited. For example, it cannot allow you to like manage the shell memory. Yeah, it's very limited in like these fine-grained operations. And the Southern Kitten is a very good example for us to have some lower level operation on GPUs. However, Southern Kitten is I need to use C++ to write Southern Kitten. I'm not very familiar with C++. Yeah, so it also makes me very, kind of hard to write in those TK kernels. And I'm very interested in like whether the infra community can come up with some other intermediate GPU programming language that is like kind of like based on Python, and it also allows us to have some low-level operations that is not achievable in Triton. Yeah. Yeah, for example, like recently, like NVIDIA has colors the Python DSL, right? And also I think another so there is also a programming language called Tileman, and it allows us to write those low-level GPU code in pure Python.
Yeah, I mean, I guess you heard her, folks. Like, which is more programming languages. I guess I see 3 more questions. So like one is on, I believe, slide 33. Maybe can we go there? '33, and then actually no, I think it might have been about 34. I think you're correct. So Acyclix is asking, any guesses at what was the cause for the inflection point on slide 33? Why is there such a sharp jump in performance?
These slides, or
I think it was slide 34, which is basically
so
like when the curve went heavily.
Okay. What's the question again?
What was the cause of this big jump in performance?
Big jump performance of which model?
I think slide 34. We're at 35 right now.
Okay, this one, right?
Yeah, like I suspect they mean when the sequence length went to 4 had them to 56, and then at sequence length 8 had them 128. Like also there was like a sharp increase when it went to 16.
I think like the sudden jump is that like because in this throughput benchmarking, when I increase the sequence length, I also lower down the batch size. Yeah. So this is actually a very good question. So in practice, right? Because for on each GPU, we can only have like so we often fix the input the number of token in the for each mini batch, right? So when we have the longer sequence, and we must to reduce the batch size for each computation, right? And for smaller sequence lengths, we have a very large batch size And in this case, this batch size this batch size dimension could provide a lot of opportunity for parallelism, right? And this is why when we increase it from 0.5K to 2K, the batch size is still, we have a larger batch size, and this batch size along with the number of height dimension could provide a sufficient amount of parallelism for computation, right? And this is why, so we do not need that much of a sequence level parallelism in this case, right? And this is very similar to the case of flash attention 1 and flash attention 2, right? Flash attention 2 has like sequence level parallelism over the query block, but this is only helpful when the number of the batch size and the number of head is their product is like smaller than the total number of streaming multiprocessor, right? And this is the case if we keep increasing the sequence length, and then the number of the batch size is like too small to provide sufficient amount of parallelism. And this is where the recurrent implementation will be much more slower. And for chunkwise implementation, since we already have the sequence level parallelism, and its speed does not influence much by increasing the sequence length. And this is why we want to have this sequence level parallelism, this chunkwise algorithm to train these models over a very long sequence training length. Yeah.
All right. I see another question from Alex Zhang. So Alex is asking, do you have any bets as a researcher for the future of architectures in 3 to 5 years? I guess I'll let you pick the time range, what you think is most interesting to make predictions on.
Yeah, this is a very high level question. So I think there are many opportunities to keep improving the architecture. I always found like the current architecture is like too simple. For example, the softmax attention mechanism is very simple. We still have the rotary position embedding, and the attention logic is computed using a simple dot product. Right? These are not that expressive. And I think I also, in the past year, I also spent some time trying to design some better position encoding scheme. Yeah, I have a recent work called Path. I designed a new contextualized position encoding scheme that is hardware efficient and allow the model to have better capacity to tackle down some a very complicated task like those involving state tracking. Yeah, so basically I designed a layer that can do better in those state tracking tasks. Yeah. So I think like for the next years, I'm very interested in designing some hardware efficient architecture that allows us to do more drafts within a single layer. So yeah, we don't need to have those like train of thought to improve the expressivity of the transformers. Although we know that like with infinite amount of like train of thought, if the train of thought length becomes like infinity, we can the transformer layer can solve arbitrary tasks, right? But in practice, this is not practical, and I want to design some more expressive layer to better tackle down some difficult problem. This is a area that interests me the most at the current moment.
So yeah, I guess we'll take 2 more questions. Tenyu Chi is asking, is there any research on distilling large language models to efficient architectures like Delta Net and Mesa Net? I know that some people are trying to do this for Mamba. So yeah, any thoughts on distillation and basically whether people should train in efficient architectures or simply distill to them?
Yeah, this is also a very relevant question. So I think like training from scratch is like too expensive. Yeah. And I think like recently there are lots of like distillation paper, but most of them trying to distill the pre-trained transformers to Mamba, right? A few papers try to distill the model to Raku 7, these more expensive layers. And yeah, I think like for academic research, it is possible. It is better to focus on like how to distilling these transformers to these efficient layers without compromising much performance. Like I think like for this kind of distillation, and the in-context retrieval is still a problem. Yeah, even though when distilling and the precision transformers to hybrid model where you have lots of global attention layer, and I in my observation is that the in-context retrieval performance could still be degraded, and it is of interesting to see whether we can use this Mesa layer to have a distilled hybrid model to see if it can improve this in-context recall performance. Because like for like a long train of thought reasoning, this in-context retrieval is very important because you don't want your model to forget the intermediate step, right? If the model does not have a good in-context retrieval ability, it will like immediately forget the intermediate result and the intermediate sort, and then it cannot have a good performance in long train of thought reasoning. Yeah.
All right, and I guess like the last question then is from Benjamin Ramati, which is, may I ask, in the in-chunk calculation with alpha t, does that work like in flash attention?
Sorry, can you say that again?
So in the in-chunk calculation with the alpha t, does that work like in flash attention?
Yeah. Let me go back to that slide. So this A, right? So for this intra-trunk computation, yeah, because the trunk size is usually small, and I can have a fused kernel to directly compute the output without materializing this intermediate local attention matrix, right? Yeah, and when the trunk size becomes larger, we can have the flash attention kernel without softmax to directly compute the output. Yeah, so basically the idea of flash attention is very general, and we can also use the flash attention idea in this context. Actually, for Mamba2 kernel, Trida already used the flash attention idea to compute this intra-trunk output. Yeah, so Mamba2's Chunkwise algorithm is very similar to this Chunkwise algorithm, except that in Mamba2 they have the additional decay term, and it is possible, totally possible to incorporate this decay term.
All right. Well, thank you so much, Songlin. It was honestly like a pleasure to have you. Like, folks, if you want to reach out more to Songlin, I think she's like fairly active on Twitter as well. Otherwise, thank you. We'll see everyone next week. Thank you, Songlin.
Okay, thank you for having me today. Bye.